We can drive that, and that's something to do with degrees of freedom. Can I explain the concept of degrees of freedom in this class? Why we call it degrees of freedom?
Not yet.
No, not yet? Okay, maybe that's a good time. Okay. So, it's related to probable degrees of freedom somehow. Let me try to explain it with degrees of freedom, and then if you have questions. Mathematically, we definitely can show. We already showed it. Okay? We already showed that mathematically, s squared, which is with n minus 1 and x bar, is unbiased, and this guy is also unbiased.
Right.
Okay? But let me start with the concept of degrees of freedom. So, if I give you this term, just this, what is the degrees of freedom for this term?
Three.
3. Why 3? Who said 3?
Why those numbers vary?
Yeah, exactly. So the degrees of freedom for this term is 3 because you can freely select any numbers for x1, x2, and x3. So I can select 5, 10, and 12 here, and the summation would be 27 in this case. Okay? Now, let me change it a little bit. What if I say this is equal to 7? What is the degrees of freedom here? 2. Why? Because you can freely select this one, any number, let's say 10, minus 5 here, any number, but the third one is not up to you. It's determined by the equation. Okay? In this case would be 2. Okay? So your degrees of freedom in this case is 2. That's the concept of degrees of freedom. And now let's see how we can explain the degrees of freedom that we had, for example, for chi-square distributions, for t distributions, and stuff. Okay? Let me start with this guy. So what is the degrees of freedom of this guy? z1 squared is 1. Okay? You can freely put any number here. Okay? What if I have, you know the distribution of this guy. It's chi-squared with k degrees of freedom. And that makes sense based on what we said. Actually, without equality. Okay? So you can freely select this one, this one, this one. So the degrees of freedom would be, in this case, k. Okay? So, but how about this guy? We say this one is chi-squared with k minus 1 degrees of freedom. Okay? N minus 1 s squared is basically, because s squared is this guy. So n minus 1 s squared is summation of xi minus x bar squared divided by sigma squared. And this is xi minus x1 minus x bar squared up to xn minus x bar squared divided by sigma squared. Okay? So how many terms do I have here? N. All right? Actually, this one is n minus 1, not k minus 1, sorry. So I have n terms here. So the degrees of freedom should be what? Should be n, right? You can freely select this one, this one, this one, this one. But it is n minus 1. Anybody knows why? Exactly. Exactly. That constraint is there because of x bar. Because we know that your x bar should be summation of xi divided by n. So you can freely select x1, you can freely select x2 up to xn minus 1. The last one should be defined by this function, by this constraint. So you are losing 1 degrees of freedom because of this constraint. Okay? Why? Because everything, write down. This should be satisfied. This should hold. Okay? So you can freely give any numbers from x1 to xn minus 1, but the last one is determined by that x bar. And that's why you are losing 1 degrees of freedom here. Okay? And your degrees of freedom instead of n is n minus 1. For t distribution, the same thing. Because you are using that chi-square distribution, the same story happens. Okay? Here also, you are not losing that degrees of freedom. Because you don't have this constraint. Okay? Mu is the population mean. So xi is your random sample. The average of x bar should not be mu. Do you know what I mean? So if I change this guy to population, then you need to basically have 1 degrees of freedom, let's say, less than this. Does it make sense? So basically, your summation of xi, I from 1 to n, divided by n, is not the mu. Okay? Because mu is the population. And you have a random sample. So you don't have this constraint. That's why you don't have n minus 1 here. You have n. Okay? Here, you have this constraint. Do you see the difference?
You're using capital N versus lowercase n. Why does that add the constraint?
If I use capital N?
Right, so mu is, if we did the whole population, it gives us the...
Exactly. If you do the whole population, then summation of xi from 1 to n, which is the whole population,
Right.
divided by n, this should be mu.
Away degree of freedom, but when we don't do the whole population, that takes away degree of freedom.
The reason is, okay, put it this way. This guy, okay, is sample average, is x bar. It's not mu, and sample average and mu are different, okay? So there is no constraint like this. The actual number that you get here is not necessarily mu. It's any number. But when you're using capital N, this has to be mu, because you are considering all the population. Does it make sense? Any other questions? Good here?
Using equations that are pretty close to the true definition of
Yes.
standard deviation, but in practice, we're not going to have the equations, and it'll be kind
In
of
practice, we cannot see a population. So that's why we use sample. Everything is based on sample. So in practice, you don't see this one. What you see is this guy. Okay?
unbiased is still a job of adjusting this.
Exactly.
the
Exactly.
numbers.
So if you do this, then it's biased estimator. Okay? And a very basically naive explanation of that would be you are losing 1 degree of freedom for x bar, so you need to subtract 1 here. Okay? But we already show mathematically why this is the case. Are we good? Everybody knows like what degrees of freedom means now? Okay? Go ahead.
Shouldn't it be that the x bar is constrained by x's, not the other way around? When you say that,
So put it this way. When you are calculating s squared, okay, you already know x bar value. Okay? So let's say somebody gives you the x bar. Then it tells you, if I give you x bar, yeah, that's the case. Okay? But so don't put it like in reality, this is not the case in reality. This is just a way of explaining how it works. Okay? But yeah, you are right. In reality, we first see the realization of basically observations and then calculate x bar. Yeah. Okay. Good. Any other questions? Good here? Okay. Variances. If you have two different estimators, you want to see which one has, and both of them are unbiased. Okay? So the one with less variance is more precise, and therefore we prefer the one with less variance. Okay? For example, both x bar and x tilde, for normal distribution, both of them are unbiased estimator for mean. However, variance of x bar is less than variance of x tilde. By the way, but x tilde, I mean median, sample median. Okay, 50% of sample is less than, 50% is higher. So that x tilde is sample median. So variance is, the first one, bias, is for mean. Second one, variance. And we had one example how we can, basically, what is the variance of x bar? We know the variance of x bar is sigma squared divided by n. So standard error would be sigma divided by square root of n. And if we don't know sigma, we can estimate that. This is what we call a standard error. Okay? So the variance of estimator, we call it the standard error of that estimator. That's the terminology. And if we estimate that, so it's going to be sample standard error or estimated standard error. We had one example. Then we said, okay, you may have a family of estimators. Okay, so let's say this is the family of estimators. All of them are unbiased. Which one is the best? The one with the minimum variance. Okay, using this basically bound, which is called Cramer-Rao bound, we can show that if one estimator is a basically unbiased estimator with minimum variance, or for short they call it minimum variance MVUE, minimum variance unbiased estimator. Okay, so let's see. Let's see if x bar is the MVUE for mu. Okay, is minimum variance unbiased estimator. So we need to show two conditions. One, it is unbiased. Second one, it satisfies Cramer-Rao bound. Okay. So the first one, we know that the expected value of x bar is mu. We already showed this several times. So the first condition, checked. Okay. So it's unbiased. Second condition, if I go back, we need to show that the variance of x bar is this guy. Okay, I'm doing this for normal distribution. Okay, this is not general. I'm just doing it for normal distribution. The reason is you need to know the PDF function of underlying population. Okay, that f of x is the PDF. So if x follows a normal distribution with this mu and sigma squared, what is basically the PDF function is 1 over 2 pi sigma exponential of this guy squared. Okay, that's the PDF function, or f of x here. So what is the next step? I need to find the natural log of f of x. Okay, so what would be that one? It's log of 2 pi sigma squared minus 1 over 2. I just a little bit changed it. But that's basically the same thing here. Plus, because we know that log of multiplication is the summation of logs. So log of exponential is going to be 1. So in this case, this would be minus half times this guy. You agree? Is it clear? Any questions so far? So what I'm doing, I am finding the natural log of the PDF function for normal distribution. Okay? So I'm trying to find the Cramer-Rao bound and then show that the variance of x bar and the Cramer-Rao bound is the same. Okay? Here is what I'm doing. So I want to find the Cramer-Rao bound and also calculate the variance of x bar and show that these two are the same. Okay? So what is the next step? Take a derivative with respect to your parameter. What is the parameter that you are interested in? Mu in this case, not sigma squared. So sigma squared is constant. You are interested in mu. So that guy just vanishes. There is no mu here. For this one, would be, let's say, something like that, probably. Always double check my calculations. I guess so. Okay? If you take a derivative with respect to mu. We're good? Which is basically x minus mu divided by sigma squared. Let me continue here. Then I need to square that, okay, this guy here, square that, and then take the expected value. So expected value of this term in our case is x minus mu squared divided by sigma to the power of 4. So this guy is constant. I can take it out. What is this guy? Definition of variance. That's the definition of variance, which is sigma squared. Okay? So it's sigma squared divided by, oh, sorry, this one is sigma to the power of 4. That's this guy. I'm just taking it out. So at the end of the day, it's 1 over sigma squared. Okay? You remember, if you look at this is 1 over n. So the Kramer-Rao bound is 1 over n expected value of which in this case would be sigma squared divided by n. You agree? I just divided by n and then reverse the everything. Okay. So now I need to show what is the variance of x bar. What is variance of x bar? We know it before. Sigma squared divided by n. That's the variance of x bar. That's the Kramer-Rao bound. They are the same thing. Therefore, based on 1 and 2, I can say x bar is MVU for mu. Okay? So that's somehow important because you want to know what would be the best estimator for this distribution. Okay? It's the minimum variance, unbiased, so in that case would be x bar. Questions? Go ahead.
Minus R.
Oh, it's Kramer-Rao. Sorry, I should have. This is this guy, Kramer-Rao bound. Let me just Kramer-Rao bound. Yeah, sorry about that. Any questions? We good? Okay. So we know that how to compare basically two estimators. First, we compare if they are which one is biased, which one is unbiased. That's the first step. Second step, if both of them are unbiased, to calculate variance. So the one with the smaller variance is the better one. What if one of them is biased, the other one is unbiased? Okay? So how we can compare them? Not necessarily the unbiased one is the better one. Okay? Let me show you some example. Look at this. So your theta 1, okay, this is distribution of your theta hat 1. This is one estimator. It's biased because it's far from basically your actual theta. Look at the distribution of your second estimator. Okay? Your second estimator is unbiased because it's exactly theta. But if you compare them, the biased one has less variance. Okay? The biased one has less variance. So what we want to do, we want to basically define a criterion which consider both bias and variance together. This criterion called mean square error. Okay? And it's basically defined by the expected value of, so your error is what? This is your estimator. This is the actual parameter. You see that? So that's the error. So that's the squared error, and that's mean. Okay? One more time. So that's your estimator. That's your true parameter. So this is error. This is a squared error. This is mean squared error because expected value is the average. Okay? That easy. And we can show that expected mean square error is basically, at the end of the day, is bias squared plus variance of your estimator. Okay? And it's easy to show. It's the expected value of x squared is always, what, do you remember? Or let me write down variance. So that's a known fact. We are going to use this fact. Variance of x is expected value of x squared minus expected value of x. The whole thing is squared. That's another definition for variance. Okay? So I'm going to use the same thing here. Or let's do it this way. Expected value of x squared would be what? Variance of x plus expected value of x squared. Okay? In this case, this would be, let's say this is your x. So your expected value of x squared, I'm sorry, this is your x. This is your x. So this is a squared. So expected value of x squared is variance of this term plus expected value of this term squared. Okay? Let's start with the variance of this term. It's the variance of the first one. This guy is constant. It's the parameter of distribution. It's not random variable. So the variance for that guy is what? What? 0. So it's variance of theta hat plus, what is this guy? Is expected value of theta hat minus expected value of a constant, not random variable. Expected value of not a random variable or deterministic variable is the same thing. Okay? This guy is squared. What is this guy? Expected value minus true parameter. Bias. That's the definition of bias. If I go back, that's the definition of bias. You can see that? Right here. Okay? So it's bias. That's why I said this is bias squared plus variance of estimator. So what you are doing, every time you calculate bias squared, the variance, and then add them up, it's called mean square error. Okay? Any questions? Are we good here? Okay. So now let's say if we want to compare two basically estimator, then what we have is relative efficiency. So the relative efficiency of theta 2 to theta 1 is MSE of theta 1 to theta 2. If you want to see which one is more efficient or better, then you calculate their corresponding MSE. The one with a smaller MSE has better efficiency. Does it make sense? That's it. Okay. Let me see. Yeah. This example, what's going on? Yep. Disconnect the cable. Okay. Oh, I'm not using a laptop. Yeah. Saying disconnected from where? Okay. Now, yeah, you're back online. Okay. So we have two estimators. Let's say we have a random population distribution we don't know, but we have two different estimators. One is basically a sample average. So we have 7 observations. We use all basically information of sample divided by 7. That's basically X bar. The second one is only using 3 out of 7 and then define this estimator. So we want to see which one is a better estimator or efficient estimator. I'll give you a couple of minutes work on that. But before working on it, intuitively, which one would be a better estimator and why? The first one, why? Because what? It's X bar, and we already showed that it has minimum variance, okay? But this is not good enough because I maybe give you something with bias, but a smaller variance than X bar. So the minimum variance theorem or Cramer-Rao bound is only valid for unbiased estimator. Don't forget that. But intuitively, I would say, again, X bar is better. Why? Exactly. I'm using better information of the sample that I have. I'm using all 7 bonds instead of using only 3 of them. Okay? Go ahead. Give you a couple of minutes. So what you need to do is basically to find efficiency for theta hat 1 and theta hat 2. These are the equations for efficiency. You already have it. So that's what you need. And see which one is more efficient. Actually, I have a class right after this, so I have to run. But no, it was just a review. It was just a review of last week. Yeah, everything is there. So it's just a review, and then as soon as you come, then we have started new material. So they already have the new material. Okay. Okay. So for the first one, it's unbiased estimator because it's x bar. So bias is equal to 0. The variance of x bar is sigma squared divided by n. So your MSE, which is bias squared plus the variance, is only variance in this case, which is sigma squared divided by n, or here we say sigma squared divided by 7. Okay? Because we have the sample size is 7. Any questions? You good here? So how about the second one? So expected value of the second estimator is the expected value of this guy which is what? Is 2 expected value of x1 minus expected value of x6 plus expected value of x4. Okay? Divided by 2, because 2 is constant. Okay? So what is the expected value of x1? X1 is, you remember, IID. X1 is random sample. Okay? A random sample definition is IID. So they have the same distribution. So x1, x2, x3, all of them have the same distribution, and their expected value is mu. Okay? So this would be 2 mu. How about the expected value of x6? Mu again, and this guy, mu. Divided by 2. So this is mu. So the second one is also unbiased estimator. Okay? Because the expected value of the second one is also mu. Let me just double check. Yeah. Okay? So bias is also 0. How about the variance? So variance of theta hat 2 is the variance of this linear combination so this is constant. I can take it out by the square that. Okay? So if the constant is a multiplier, I can take it out of the variance by a squared that. Variance of 2x1, this negative would be what? Positive plus variance of x4. Okay? Is it clear? Any questions here? So this is a multiplier. Take it out, we square this. So we know that the variance of any linear combination is the linear combination of the variance, but squared the coefficient. So this guy squared would be positive. That's why I have positive here. Okay? So for the first one is 4 variance of x1 plus variance of x6 variance of x4. So what is variance of x1? Is what? Sigma squared. This is also sigma squared. This is also sigma squared, which would be 6 sigma squared divided by 4, 3 sigma squared over 2. Okay? By the way, this is correct because they are independent. That's the definition of random sample. Otherwise, this is not correct. Otherwise, we need to have some covariance parameter or terms as well. Any questions? Is it clear? So what is MSE for? Basically, MSE for theta hat 2 is the bias, which is 0, and variance. So which one is more efficient? Oh, by the way, our n is, in this case, is what? 7. Oh, I'm sorry, this is not n, sorry. Messed it up. This is 2. I solve it like specifically. I didn't solve it generally. So it's 3 sigma squared divided by 2, and the other one is sigma squared divided by 7. So MSE of theta 1 is sigma squared divided by 7. MSE of theta hat 2 is 3 sigma squared divided by 2. Definitely, this one is smaller. Therefore, the first one is more efficient. Any questions? Yeah, go ahead.
Bar for the first one and not
Because that's the definition of X bar.
the sum?
Yeah, summation of xi divided by n. All right?
Okay, because it's all 7 samples.
Exactly.
Okay.
Because we already have like 7 samples. Any other questions? Okay. So I'll give you time probably. You work on it at home. I'll try to solve it on Wednesday. Just give you a hint. What you need to do, you need to find the expected value and variance of a uniform distribution first. Okay, for this example. Expected value and variance of a uniform distribution with these parameters. That's what you need. That's the first step. And then try to solve these two basically parts. So before doing that, you need to find what is the expected value of, what is basically mu for uniform, and what is sigma squared for uniform. Okay? Definitely it's a function of theta. That I can tell. So this example, it's also a very interesting example. I give you two basically sample variance, two different versions of sample variance. One is definitely unbiased. The other one is biased. I want to know which one is more efficient. Okay? But here is one more piece of information. They're coming from a normal distribution. That would help a lot. It's kind of like simplify very long solution into probably 2 or 3 lines solution. Okay? I'll give you a couple of minutes actually. So we have 4 minutes. I'll give you 2. Just a small hint, if you have a chi-square distribution, let's say, I don't know, let's call V, has a chi-square distribution with k degrees of freedom, expected value of this chi-square distribution is what? It's k. The variance is, anybody remembers? What? I'm hearing something which sounds correct. Is what? 2k. Okay? That's a piece of information that you need to use.
That
Any random variable.
variance.
No, any random variable that has a chi-square distribution with k degrees of freedom has this basically expected value and variance. For the first one, I already know this is unbiased estimator, which is sigma squared. So bias is 0. Okay? Actually, if we want to show that, I can write this down as this. So what I'm going to do, I want to use this guy. So I'm trying to make this as a chi-square distribution. Okay? You remember n minus 1 s squared divided by sigma squared is a chi-square distribution? So I multiply this. Also, at the same time, multiply inverse of it to make it basically, they cancel out each other. So this is constant multiplier. I take it out. At the end of the day, I get this guy. Okay? So what is this? It's chi squared with n minus 1 degrees of freedom. So the expected value of this guy is n minus 1. I cancel out n minus 1 with this n minus 1. At the end of the day, I get sigma squared. Okay? That's easy. Let me do this for variance as well, and then for the second one, we can continue on Wednesday. So for the variance, I'm going to do the same thing. So this is constant. Taking out should be squared, because that's variance. So it's sigma power of 4 n minus 1 squared. Variance of this guy is a chi squared with n minus 1 degrees of freedom. So variance of a chi squared with n minus 1 degrees of freedom is what? Or let me write it down. Yes, it's 2 times n minus 1 based on this guy. Okay? Then, is this sigma 4? Yeah. Sigma to the power of 4. I can cancel out this. So it's sigma 4, 2 sigma 4 divided by n minus 1. That's the basically mean variance, and this is bias. So your MSE for sigma hat 1 would be 0 squared plus variance, which is 2 sigma 4 n minus 1. That's for the first one. Second one, we can do the same. Very similar, you know. You just have n here. You need to basically change it to n minus 1. That's something else that you need to multiply. Okay, I'll solve this one on Wednesday. Have a good one.